Nowadays, practically everyone who sees movies, science fiction movies, knows a little bit about the theory of relativity. They know, for example, that when you go through space very fast, then time begins to slow down. And they know that when you finally travel through space at the speed of light, supposedly time stops. And a lot of people even know that if you see a spaceship going through space fast, the spaceship seems to shrink. And finally, when the spaceship goes through space at the speed of light, the spaceship shrinks so much that it vanishes. But the thing that bothers a lot of people is they don't know why these things happen. And the explanation is usually something like this. Well, you assume that a thing can't go faster than the speed of light, and you assume that the world looks the same for everybody, and then these weird consequences of time going slow and such things follows as a logical necessity from that. And it's all derived by some mathematical process. But it still leaves people with an inquiring mind, with a curiosity about what really makes space shrink, what really makes time go slow. You might ask, what do these people really want? What do they want for an explanation of the reason? What people really want is a little myth or a little story. Now, you might think myths and stories are not appropriate for physics, but in fact, myths and stories are used all over physics. Let me give you some examples of places in physics where myths and stories are used. How do people explain electrostatics? By a little sex myth that opposites attract and that likes repel. Isn't that the standard way for explaining electrostatics? How do people explain things like the second law of thermodynamics, that if you have two gases and they're put together, after a while the two gases get mixed up, or if you have a hot gas and a cold gas, after a while they get mixed up and you have a medium gas. They explain it by Murphy's Law, isn't that right? That if the darn thing, anything that can get mixed up will get mixed up, and therefore the gases get mixed up. And physicists are always explaining things like conservation of energy or conservation of momentum by the fact that God doesn't want to waste things. Forces are represented by arrows, but a force, of course, is not really an arrow. That's just a nice little image that you can put up in your mind, a nice little myth, as it were. Of course, not any myth will work. You can't use any myth you want. There's one thing that the myth has to have, and if you choose a myth, what follows from the myth has to actually be found in nature, and what's found in nature has to be explained by the myth. And if you get a good myth, the good myth will work for this. So what is really needed to make people understand about relativity is a good myth for special relativity. The question that perpetually plagues people with an inquiring mind who read and think about relativity is why it is that you can't go faster than the speed of light. What is it that doesn't allow you to go faster than the speed of light? And you can make up a little story or a little myth that will explain that, and also in the process explain all of special relativity. And the little story goes like this. The reason that you can't go faster than the speed of light is that you can't go slower than the speed of light. In fact, everything is always moving at the speed of light through space-time. You say, well, look, I'm sitting in a chair. If I'm sitting in a chair, then certainly I'm not going at the speed of light. Yes, you are. When you're sitting in a chair, you're going at the speed of light through time. Sounds awful strange, but I can make it sound less strange by drawing a diagram. And here, let me show you the first picture. Here is a diagram, and in this direction, we go through time. So that as a thing gets older, it just goes through time. And the object that I've drawn here, represented by this arrow, is just going through time. Notice it's not moving through space at all. Space is in this direction, but it doesn't move this way at all. It just goes through time. Now, let me draw another object that is actually moving through space a little bit. And I will represent that object by this arrow. Now let's look at what's happening here. This object is moving through space because it begins here at this part of space, and after a while, it's moved over this far in space. And it's also going through time too. But we've kept its speed constant, which means that this arrow is just as long as the other arrow was to begin with. And what's the consequence of that? Now, when it's going through space, it's less able to go through time, and notice that the amount of time that it's gone through is less than if the object was standing still. What happens as the object goes faster? If it goes faster, it goes through more space, but as it goes through more space, it's able to go through less time. Finally, in the extreme case, how fast can an object possibly go? Well, it can use all of its speed for going through space. But look, if it uses all of its speed through going through space, how much speed has it got left for going through time? None at all. And this illustrates the idea that everybody knows from science fiction, that if the speed of an object begins going through space as fast as it can, which is of course the speed of light, then it doesn't go through time at all. And here you see it goes along here, but it doesn't age at all. Now there's an important idea that I want to put out here. It's true that for the objects I've illustrated here, you see them going through time more slowly. But the question comes, if you yourself were going through space at the speed of light, or at half the speed of light, would you see yourself aging more slowly? And the answer is no, you would not. Why is that? The answer is because you see these objects going through space. Can you ever see yourself going through space? The answer is you can't get away from yourself. As you see yourself, you always keep a constant distance from your own nose. Therefore, as you see yourself, you are never moving through space. Therefore, you must always see yourself moving through time, and so you cannot see time for you running slow. Even though you can see time for me running slow, and I can see time for you running slow, I can never see time for myself running slow, or you can never see time for yourself running slow. Now, in a lot of science fiction stories, people wonder how the world would be or how the world would look and feel to move at the speed of light. And in fact, you are moving at the speed of light right now. And if you want to know how it would feel, I can ask you, because right now you are moving at the speed of light. And it is that effect of moving at the speed of light that gives you the sensation of time. Finally, I'd like to show you something else. There are many ways to answer a question, and there is still another way to answer the question of why you can't go faster than the speed of light. In fact, the way of the guru, the guru, when you ask the guru a question, the guru answers by asking you another question. And if anybody should ever ask you why you can't go faster through space than the speed of light, you might ask them back, well, why can't you go faster through time? There are a lot of situations when you'd like to go through time faster, like, suppose you're being kept in jail and you know bail is coming, but you wish it would come faster. You're being kept after school and you know sooner or later you're going to get out, but you wish time would go by faster. If anyone could ever invent a way to go through time faster, they would automatically invent a way to go through space faster. And let me show you with this diagram. What would it mean to go through time faster? Well, this person's going through time at a certain speed represented by the length of that arrow. And if you could go through time faster, that would mean you'd go like this. Instead of going from here to here, you'd go from here up to here. Well, if you could increase the length of this arrow, you could also go this way faster. And you'd go this way faster. And eventually go this way faster. And finally, you could go through space faster. So, if anybody ever invents a way to go through time faster, they'll automatically invent a way to go through space faster. And conversely, if anybody ever discovered a way to go through space faster than the speed of light, they would also have invented a way to go through time faster. But to date, nobody's invented a way to do either one. Now, I'm going to show you a simple use that this way of thinking about the world has. I think that everybody by this time has heard of the so-called twins paradox in relativity. The story is that there are two identical twins, of course they're both the same age, and one twin stays at home, does nothing. The other twin gets in a spaceship and zooms out into space, and after a few years zooms back again, traveling very close to the speed of light, and lo and behold, the twin that returns back home turns out to be younger than the twin who has stayed at home doing nothing. And it seems really weird. How are you to picture a situation like that? And I'd like to show you an easy way that you can picture that situation, which makes it all kind of clear. Here on the second diagram, I have that situation. And first, this line corresponds to the twin that is staying at home. And each little arrow corresponds to a year. And that's 1 year, 2 years, 3 years, 4 years, 5 years, 6, 7, 8. After 8 years, the twin has gone through this much time and is up here. This is the twin that stayed at home. Now let's take the twin that went out into space in a spaceship. That's this twin here. 1 year, 2 year, 3, 4, 5, 6, 7, 8 years. Notice that each of these arrows for the traveling twin, each year, is just as long as this twin. So this twin's speed through space-time is just as much as the stay-at-home twin. The only thing is that the twin that's going out, this twin is traveling. See, they start out together, but this twin goes out into space, then stands still, and finally comes back, and finally he's back home again. But lo and behold, after we've watched 8 years go by, how much has the traveling twin gone through time? Not as much as the twin that stays home. What does it mean that this twin who went out in space is falling behind here? What does this mean that this twin has fallen behind? This distance means that the traveling twin has actually come back younger, and in the diagram that I have it's about 1.5 years. He's about 1.5 years younger than his brother who stayed at home by virtue of the fact that he used his speed to travel through space and not to travel through time. Okay, good enough. Now, I've finished an idea, and I want to give you a little quiz to show you, see what you have learned. I want to ask you this question. Suppose there is someone, and that person is traveling through space at half the speed of light. How fast are they traveling through time? What's their speed through time? Well, you might begin and you would think, well, gee whiz, if you're going through space at half the speed of light, and you'll go through time more slowly, of course, and since you're going through space at half the speed of light, maybe you're going through time at half the normal speed too. You've divided your speed in half, using half of it for space and half of it for time travel, and maybe that's what you're doing. But it works out that it's not quite that way, and I'd like to show you a diagram that illustrates the situation. Here in this diagram is time running this way and space running this way. I haven't written down time, but it's the same as all the other diagrams. And this arrow represents an object which is going through space at half the speed of light. Why is that? Because if it was going through space at the full speed of light, it would go this far, and if it's going through space at half the speed of light, then in that amount of time it goes only half as far. And so this object goes half. It represents an object that goes going at half the speed of light. Now, how fast is that object going through time? Well, it's going through time, while it gets going at half the speed of light, the amount of time that it goes through is this amount of time right here. Had the object been standing still, it would have gone through this amount of time, and so it's going a little bit less than the speed. Its speed through time is a little bit less than the speed that it would have if it were standing still. How much less? How much less? Well, I've divided this thing up, and I have here 1, 2, 3, 4, 5, 6 units. Were it standing still, it would have gone through about 6 units of time. Because it's moving at half the speed of light, it doesn't extend through 6 units of time. It only extends through about 5 units of time. What that means is that if you were to watch an object age, and the object, as you watched it, were traveling through space at half the speed of light, then the object would age at approximately 5/6 of its normal rate of aging. What does 5/6 of its normal rate of aging mean? That means that if 60 minutes went by for you, for the object that you watched, only 50 minutes would go by. Not very much difference. Even at half the speed of light, time is going slow for the object, but it's really a relatively small effect. Before time can really slow down for that object, it has to really get up a lot closer to the speed of light than just half the speed of light. In fact, that's probably why it took so long for relativistic effects to be discovered, because they're not very pronounced at small speeds. Now, I would like to put a question to you, and this question is, suppose you want an object to travel through space, and you want it to go through space so fast that for its clocks will seem to be running at half their normal speed. How fast will that object have to go through space? Well, you think a little bit, and it turns out that the diagram just flips like this. You would just put in an arrow down here, like so, And now, if an object moved like this, it would go through only 3 units of time. How fast would it be going through space? Well, 5/6, isn't that right? It would have to go at 5/6 the speed of light in order that it should go through space at half the normal speed, so that its clocks would read 30 minutes in the time that your clock would have gone through 60 minutes. It's interesting when you did this, most people will see this right away, but what they do in their mind, it's the first time that you begin to treat what you knew about space, what you knew about time, you begin to use on space, and what you use on space, you begin to use on time. You just flip the space and time axis, and so you see the answer comes out. And you see that now you begin to think mathematically, and as you think mathematically this way, you begin to think of space as being something like time, and time as being something like space. Now, I want to show you how the diagram that we've used so far can be made more realistic. So far, we've talked about a diagram in which time ran just in one direction, and space ran in just another direction. But that's not very realistic. Of course, space not only can run this way, but of course space can run the other way too. In fact, to make the thing still more realistic, what we should do is have sort of a flat surface here so that we can have space with 2 dimensions, and then time would come like this. And we can represent kind of a flat space of the world. And it makes the thing look more like the real world. If we go to this kind of a diagram, then what we have to do is say that if you're standing still, you're just going through time, and you're going like this, from here up to here. If you begin to travel through space, then you go like this, or like this. And as you go over through space, and you're moving to the right here, you're going through time more slowly. And if you were to travel at the speed of light, then of course you'd just be going in a direction like this. You'd just be going through space, and you would not be going through time at all, and you'd have a choice of directions. And this is not very bad representation of the world, because on this, as I said, on this flat surface here, you can draw maps, and people frequently do think of the whole world as just a map, and the diagram allows that. Now that I've gone that far, I'd like to ask 2 seldom asked but salient questions. Why is it that when God created the world, He actually made several space dimensions, in fact, 3 dimensions of space, but only 1 dimension of time? Why didn't God decide, well, look, I'll make 3 dimensions of time and 1 dimension of space? Or why didn't God say, look, I'm going to be fair. I'm going to make 2 dimensions of time and 2 dimensions of space? Why is it that the world is put together that way? You see, it's a fair question to ask, because you remember earlier on, we saw that time was very much like space, and you could easily answer certain questions just by switching time and space. So time is not that much different from space, and it's a fair question. Why 1 dimension of time and 3 dimensions of space? And another seldom asked but important question is this: why is it that people are free to move in space? You can move to the right, you can move to the left, you can move forwards, you can move backwards, but in time, you're carried forward relentlessly at 1 speed in 1 direction, and you have no choice. Why is travel through time so different than travel through space? I want now to extend the myth, to explain why it is that you're drawn through time in 1 direction relentlessly at 1 speed and have no choice, whereas you can move through space in various directions, and why it is that time has 1 dimension while in space there are 2 or 3 dimensions perhaps. Why is that? I will make up a little extension of the myth. In the beginning, when God created the world had 4 dimensions, and the 4 dimensions were all alike and undistinguished from each other. That is, all 4 dimensions were the same. There was no time and there was no space. And then God created atoms and electrons and photons, and He embedded them in the space. And of course, like all things, these things had to move at the speed of light through space-time. Now, as you know, when a thing begins to go faster and faster, space shrinks more and more. And when finally a thing goes at the speed of light, space in the direction that the thing is going shrinks so much that space in that direction ceases to vanish. So for every individual particle in the universe moving at the speed of light in some direction through space-time, that particle will lose the dimension in the direction that it's going. One dimension will completely wipe out by virtue of the fact that it's going at the speed of light. So if you have 4 dimensions and you subtract 1, 4 minus 1 is 3. And for each particle, as it sees the world, the only dimensions that are left are those 3 dimensions that are perpendicular to the direction that it's going through space-time. And so it sees those 3 dimensions and calls that space. And the ghost of the 4th dimension that's lost in the direction that it's going, that becomes felt by the particle as the current of time. Now, all the particles in the universe are headed in different directions, and therefore each one takes the direction that it's headed in as the proper direction of time. But since different ones are going in different ways, everybody slightly differs from everybody else as to what the proper measure of time is. Now, if you can understand how an object is oriented in 4 dimensions, then you can figure what its projection must be in 3 dimensions, that is, what its shadow cast into 3 dimensions is. And we can understand the way objects appear in space as just the shadow of a 4-dimensional object. If we know how to carry out the shadow casting process, we can figure out how objects appear in the world. And I would like to show you how to do that process. And as an example of an object in space, I've picked an object that's always represented sometimes as the world, which is the United States of America. And here behind me is a picture of the United States of America. And here, in this first picture, the United States of America is just going through time. You're just seeing the country standing still. And as time goes on, of course, the United States will age, which means that it will move up through time. Of course, we see the space. This is our space back here. And as we watch the United States, we do not truly see the 4-dimensional United States. We only see its extent in space, which we'd call a map or a photograph, which is really the shadow down here. But notice, as the object moves this way through time, the shadow looks just like the country. It's an exact silhouette of the country. Nothing happens. Except, of course, the country, that everybody gets older as you watch. It doesn't move through space, but everybody and everything will age. Now, how would it look in the event that you saw the United States in motion? Of course, by the way, there are 2 ways to set the United States in motion. One way, you could set the whole country moving through space, or another equivalent way, you could let the country stand still and you could move yourself. That would also work. Here in the second picture, I've shown what the world would look like if the United States were seen not at rest, but were seen in motion. Incidentally, there are 2 ways to put the United States in motion. One is physically to pick up the country and set it in motion. And the other way is to leave the country alone, but to move yourself. Either way, as far as you're concerned, it will seem that the country is moving. And the particular way that I've set the United States moving is to the east. You see here, this arrow shows that the United States is moving through time. That means everybody is getting older. But the arrow is also tipped a little bit this way towards the east, which means that the whole country is going to move this way. And therefore, as you see the shadow of the country, which means how it appears in space, you'll see that the shadow is drifting off in the easterly direction. Now, let's look at a few things about that. The proper space of the United States, remember the story, is that in the direction you're going, that's time, but what's left of space is always perpendicular to time. And here's the space of the United States, and the space of the United States must be perpendicular to the direction that it's going through time. So when the country is set in motion, the country itself must be tilted. What consequences does that have? I'd like to show you what consequences that has. Well, it has these consequences. Here, when the United States was standing still, if you were to look down at the country, and there was to be a person talking to a person in New York, and they were to be on a telephone, you would see that the person in San Francisco and the person in New York were having a telephone conversation, and you would see it both at exactly the same time. Here, if you were to look at the country, when you see the country in motion, you get the strange effect of the desynchronization of time, and the event, while 2 events might be happening at the same time on the country itself, as far as they were concerned, you would see the event in San Francisco seem to happen ahead of the event in New York. You see that they're desynchronized in time by virtue of the fact that the country is tilted. And another thing happens because of that, and that is this. If you look at the country as projected into your space, you have to take the shadow of the country. And here, down here, is the shadow of the country. And when it's in motion, the shadow has to shrink. Not all dimensions of the shadow shrink, but if it's moving to the east, the dimension from New York to San Francisco shrinks. So the country appears to shrink in this direction, east-west. But if you say take the direction from Chicago down to Dallas, that dimension does not shrink because the country is moving in the east-west direction. It's not moving in the north-south dimension. You can see what's going to happen here. If you make the United States go, imagine the United States is seen moving to the east faster still. Well, then you would, of course, have to tip this arrow even more. And as you tip this arrow even more, you make it go to the east faster, but in consequence, you make it go through time even more slowly. And also, the surface of the United States is tipped like this, even more steeply, so its shadow becomes even more contracted. And in the extreme case, if the United States is finally moving at the speed of light to the east, then in that event, it's not going through time at all. The United States is tipped exactly like this, and its shadow vanishes. And everybody knows that when you see a spaceship move at the speed of light, or anything move at the speed of light, the thing vanishes. And of course, the reason is that the shadow would be seen edge on, like Saturn's rings, edge on, vanish. Well, there in one picture, summed up, is the whole special theory of relativity. And I'd now like to come back to kind of a philosophical question, to ask you, is this myth that I've given you real? Is it really true that an object is always moving through space-time at the speed of light? And is that really true? 500 years ago, a similar question was put to Nicholas Copernicus. They asked Nicholas Copernicus, they said, is the Earth really truly moving through space the way you say it is? And either Nicholas Copernicus or one of his assistants came up with this answer. He said, it is ridiculous to believe that the massive Earth could really be moving through space. And with that, moving perpetually, never slowing down. But Copernicus said, if you will just pretend, imagine that it's moving through space, then it makes the workings of the solar system easier to visualize and the calculations easier to do. And I think that Copernicus's 500-year-old answer will also suffice for the myth for relativity.